Okay, so this section is on defining the term stoichiometry. This is going to set the framework up for section 3, which we're actually going to apply it a little bit more. But today we're going to learn about what it is and then how to determine ratios from our balanced equations. So we're going to use section 1 with balancing to help us out here with section 2. So what's the value of having a balanced equation? Well, it tells you the relative amounts of each substance present during a reaction. Okay, I'll explain what that means here as we go. The coefficients in front of the substances. Okay, all the coefficients, the 2, the 3, and the 2 in that example right underneath there. The coefficients represent the mole ratios. Okay, mole ratios. So that'll mean if for every 2 moles of iron in this reaction, I need 3 moles of fluorine gas to react with it. Moles, not mass. So it's not 2 grams of iron with 3 grams of fluorine gas. Okay, that's not how it works. It is for mole ratios. It also tells you how much you can produce. If you've got 2 moles of iron, you can make 2 moles of iron 3 fluoride. So that's what this is saying down here. For every 2 moles of iron, you can have 2 moles of FeF3. For every 3 moles of F2 you could produce a maximum of 2 moles of FeF3. Okay. These ratios can be used to determine the relative amounts of substances. Section 3 is going to deal heavily with this. Okay, it'll be how to convert between this substance to this substance. How much are you going to need to make this much product? That's what the goal of stoichiometry is. So, the technical definition here, the study of the quantitative relationships between the amounts of reactants used and amounts of products formed by a chemical reaction. Okay, so you're trying to figure out how much you need, how much stuff do you want to make. Sometimes it's compared to like a recipe like baking cookies, how much sugar, how much butter, how many chocolate chips, how much vanilla, whatever. But there's a certain ratio in which all those things need to be added together if you want to make a certain amount at the end. So it's kind of, you might think of it sort of like that. But we're dealing with chemicals, so how much of this chemical in both mass and in moles. This is all based on the law of conservation of mass. Remember, we can't create or destroy matter. It's got to go somewhere. So we got to account for it some way or another. So here's an example over on the right. So if we take, for instance, iron shavings, little tiny pieces of iron, and we were to put them, say, into a Bunsen burner or something that is on fire. It will react with the oxygen around it. It will spark very, very nicely like that. And instead of just having iron metal, what you will get when all these particles fall to the ground and sit here on the bottom, that is rust. Iron 3 oxide is rust, Fe2O3. That's the reddish powder. Well, this reaction has the ratios you see up here. For every 4 moles of iron, you need 3 moles of oxygen gas, and that would produce 2 moles of iron 3 oxide, or rust. So for every 4 moles of Fe used in the reaction, 2 moles of Fe2O3 can be produced. It's a 4-to-2 ratio, or simply a 2-to-1 ratio. Okay, so if you had 1 mole of Fe, you'd make half a mole of rust, Fe2O3. So if you had, say, 8 moles of Fe used in the reaction, then you'd only make 4 moles of Fe2O3. Once again, that's at 2-to-1 or 4-to-2 ratio, okay, based on your balanced equation. But notice, up here, these 3, that is in the lowest possible whole number ratio, 4-to-3-to-2. I can't reduce that anymore. There's no smaller whole number ratios for those coefficients. So, mole ratios. This is very important to understand what is going on with mole ratios, because without it, you're not going to have any idea what stoichiometry is doing. It's a ratio between the numbers of moles of any 2 substances in a balanced chemical equation. Basically, what we're going to do is make fractions and use them just like we did in Unit 1 as conversion factors, going from one substance to another. Going from one substance to another. So If we take the example here of this reaction with potassium reacting with liquid bromine, remember it's diatomic, so it's Br2, yielding 2 potassium bromide. Okay, that's a solid, it's a salt. For every 2 moles of potassium, 1 mole of bromine is needed, Br2. Remember, if there is no coefficient there, that is simply a 1. Okay, so for every 2 moles of potassium, you need 1 mole of bromine. Or, if we're writing it as a conversion factor, going back to Unit 1, 2 moles of potassium per every 1 mole of bromine. Or, same thing, you can flip that because they're the same value, 1 mole of bromine for every 2 moles of potassium. This will be used as a conversion factor. You've seen these before. Hopefully, this is not anything new to you. These are equivalent amounts, so we use them again as conversion factors. Also, for every 2 moles of potassium that you have, you could make 2 moles of potassium bromide. So same thing, 2 moles of K for every 2 moles of KBr, and you could flip that 2 moles of KBr for every 2 moles of K. Continuing on with that example, you can also do the same thing there for bromine. All right, for every 1 mole of bromine, you can make 2 moles of KBr. You could write that either way here, 1 Br2 over 2 KBr, or 2 KBr over 1 Br2, because again, these are conversion factors. Hopefully that term is coming back to you from Unit 1, conversion factors. So you can flip them because they mean the same thing. So, let's try this. Balance the following reaction. Use the law of conservation of mass to check your answer. Basically, what we're going to do is do this, and then we're going to write out all of our ratios. So, on the left-hand side, I have 1 sodium, 2 hydrogens, and 1 oxygen. On the right-hand side, we have 1 sodium, 1 oxygen, 1 hydrogen, plus 2 more, so we got 3 hydrogens. Okay, so we're going to need to do a little bit of reasoning here. Sodium is all the same. The oxygen is the same. The hydrogen is not. So we got to come up with a way to balance that. Well, over here on the right, we have more of it than we do over here on the left. So let's just go ahead and see what happens if we say, take for instance, and put, I don't know, how about a 2 in front of the H2O and see what we get. So if we do that, we've now doubled the amount of hydrogen, so now we will have 4. And we will also now have double the amount of oxygen, so now we have 2 oxygen. If we come back over here to the right side, all right, we've got 3 hydrogen. Now we've got less hydrogen over here than we had over on the left, but we can fix that. Why don't we try putting a 2 in front of the NaOH? And if I do that, I now double everything after it, so I have 2 sodiums. I have 2 oxygens now. And the hydrogen, remember there's 2 over here, and I've got 2 here now, so that will be a grand total of 4 hydrogens. So we're getting closer. The hydrogens now match. The oxygens now match. The sodiums don't match yet, but that's an easy fix. All we got to do, if we put a 2 in front of the sodium over there on the far left of the reactants, we'll end up with 2 sodiums. Okay, so just double checking here our work. We got 2 sodiums, 4 hydrogens, 2 oxygens, 2 sodiums, 2 oxygens, and 2 plus 2 is 4 hydrogens, so that balances that out. 2, 2, 2, 1. Okay, so if we write those values in here, okay, and if it's a 1, you don't have to write it. I just did for the sake of having that number in there. Okay, so now we want to write out all the possible ratios. Well, we could have 2 sodium for every 2 water, which is the same thing as 2 H2O for every 2 sodiums, because they mean the same thing. You could have 2 sodiums for every 2 sodium hydroxides. And the reverse is also true, the inverse, I suppose. There we go. We could have 2 sodiums for every 1 hydrogen, or 1 hydrogen for every 2 sodium. So this one is not just a 1-to-1 ratio. Notice all these cancel out basically to be the value of 1, but here you have a 2-to-1 or a 1-to-2 type of ratio. We could also have 2 H2O for every 2 NaOH, and the inverse of that is also true. We could have 2 waters for every 1 hydrogen, or 1 hydrogen for every 2 waters. And we've got one final option here, one combination that has not yet happened, and that is if we have 2 sodium hydroxides for every 1 hydrogen, which is equal to 1 hydrogen for every 2 sodium hydroxides. These are all the possible ratios that could come out of this. So if I have 2 moles of sodium, I need 2 moles of water to react with that. If I've got 2 moles of sodium, I can produce 1 mole of hydrogen gas. Okay, so that's what this value is here. This is where stoichiometry is heading towards. We're not quite yet at what it's going to involve, but we're getting very close. Okay, one more example. Balance it and then determine the possible ratios just like we did. Okay, so let's see here. So we got zinc. We got 1 zinc on the left, 1 oxygen. Whoops, let me undo that. 1 oxygen. We got 1 hydrogen and 1 chlorine, so 1's across the board. And then on this side, 1 zinc, 2 chlorines. We've got 2 hydrogens and 1 oxygen. Okay, so we don't start with hydrogen or oxygen. We're going to start with the chlorine situation. So we got 2 over here and 1 over here, so we will put a 2 in front of that, which will give us 2 chlorines. It will also give us now 2 hydrogens. Okay, and just checking, zincs are now balanced, chlorines are now balanced, hydrogens are now balanced, oxygen's balanced. So all we had to do was put a 2 in front of the HCl. So to write the ratios for this, we'll need to use the 1 zinc oxide for every 2 HCl, or every 2 HCl is 1 zinc oxide. 1 zinc oxide for every 1 zinc chloride is equal to 1 zinc chloride for every 1 zinc oxide. And we'll keep going here. For every 1 water molecule, and 1 water for every 1 zinc oxide. And for every 2 HCl, you can make 1 mole of zinc chloride. For every 2 HCl. Okay, so just reversing that, we could do 2 HCl for every 1 water that we form, or we form 1 water for every 2 moles of HCl that we've got. And our final option can have 1 zinc chloride for every 1 H2O, and 1 H2O for every 1 zinc chloride. Okay, so those are the possible mole ratios. Got 6 of them there, 6 possibilities. So there's no assignment listed for this. However, you need to know how to write these. You absolutely have to know how to write these, because when we get to section 3, you're going to need to decide which one you need to use to get to the answer that you'd like.